Introduction, Materials, and Procedure. Students will pull weighted objects across different surfaces. They will measure the force that it takes to just move the object and then the force it takes to keep it moving at a constant speed, which means your acceleration is 0. Students will use these data to find the force of friction and then find the coefficient of friction between the surface and the object using the algebraic approach. Here are the materials. We'll have surface and an object, masses to put on the objects, and a spring scale, or anything that can be used to measure the force applied to an object. The following items should be prepared before the students arrive. Set up your stations with different textured objects and different textured surfaces. Include spring scales and masses to change the weight of the object. And here's an example of what a spring scale looks like, and they're either calibrated in grams, in which case you have to multiply by 9.8 meters per second squared to get the force in newtons, or they might be calibrated right away in newtons. Boxes with different bases should be purchased by the school, or you can be creative and use your own. See the Mushu lab on NJCTL.org. Whatever type of surface you use, be sure that the spring scale can be easily hooked onto it. So you have like little loop there, and this one you would hook it over to there. The procedure for the students. Measure the weight of the object and record in your data table, and that should be in newtons. Okay, so it's going to be force G or W, and that's equal to mg, and make sure you know what your scale is giving it to you, either in grams or in newtons. And of course, if you measure in grams, I said you just multiply by 9.8 meters per second squared, but what do you have to do with the mass in grams? You have to convert that to kilograms first. Attach the object to the spring scale and pull so that the object is moving at a constant speed. Make sure that the spring scale is horizontal. The force will be less if you are pulling at an angle, so you don't want that. Some of your force will be going into the Y direction, and we're not doing that in this class. Carefully read the applied force from the spring scale while you're pulling at a constant speed. Record the force in your data table. Add additional weight to your object and repeat to get 5 data points. Now switch and follow the same procedure for 2 new object surface combinations. Some warnings for the lab. Make sure the spring scale is calibrated to 0 when nothing is hanging on it. The nut at the top of the spring scale can be twisted to raise or lower the spring. Check the units. Okay, we've said that a couple times. Because the conversion between weight and mass is just multiplying by G, many spring scales show weight on one side and mass on the other. You should be recording the weight. That's the force. And again, if you've got grams, you have to convert the grams to kilograms and then multiply by G. Make sure the surface is long enough so that you can pull across it with a constant velocity, because you're going to be accelerating it first from 0. That's not what we want. You need to have it at a constant velocity, which is going to take a little bit of time. Make sure the surface is long enough. Ensure your spring scale is aligned horizontally. You want all the force in the X direction. You don't want anything going in the Y direction. Spring scales are not accurate at small extensions. If your object is very lightweight, then just add mass for the first trial. Here's an example for a 100-gram mass. You have to convert the mass first to kilograms. So there's 1,000 grams in a kilogram, so 100 grams would be 0.1 kilogram. You multiply it by the acceleration due to gravity, and you get a weight of 0.98 newtons. So if you're adding 100 grams to your object each time, you can approximate the added weight as 1 newton for simplicity's sake. This will have a very small effect on your results. Makes it a little easier. Spring scales come in different colors representing different maximum weights and force. If your spring is extended past the maximum value printed on the scale, then you're using too much weight. Either get a spring scale with a larger maximum weight or apply less weight to the object. The free body diagram for an object being pulled across a surface at a constant velocity looks like this. The horizontal forces should balance each other, and the vertical forces should balance each other. Therefore, there is no net force and no acceleration, constant velocity. This is key to the lab. Notice how the magnitude of this vector is equal to this one. That means they're equal magnitudes. They have the same size vector and opposite directions, so they'll cancel out. Same with the normal in mg. Because there is no acceleration in the y direction, the normal force equals mg. And that means it's not bouncing up and down, it's just sliding along the surface, not moving up and down in any way. The applied force, which is read from the spring scale, which is what you're doing to pull the object, you've got the spring scale hooked up to the object, that's equal to the friction force because there is no acceleration in the x direction as long as your velocity is constant, which is how you want to pull it. What are we actually measuring here? We're measuring the applied force with the spring scale as we pull the object, and hopefully earlier, and if you haven't, do it now, we measured the weight by hanging the mass on the spring scale. We will be calculating the friction force and the normal force by just saying that if we're pulling at a constant velocity, the friction force will equal the measured applied force, and the normal force will equal the measured weight. Written instructions are very handy, but it's always great to see the lab actually performed. So please click here to see the lab in action.